Welcome, students! In this session, we are going to do a quick but thorough revision of the entire Metals and Nonmetals chapter. Now, this is designed to help you with your final board exam preparations. Think of this as a checklist, a way to quickly refresh all the important concepts and maybe spot any areas where you need a little more practice. So let's begin. So, here is our roadmap for today. We will start with the basics, the differences between metals and nonmetals. Then we will dive into their chemical reactions and that very important reactivity series. After that, we will understand ionic bonds, how metals are extracted, and finally, we will finish up with corrosion and some really crucial tips for your exam success. All right, let's get started. First up, we'll do a quick recap of the physical properties. These are the properties that really create that clear separation between what we call a metal and a nonmetal. Let's quickly go over the key differences. So on the left, we have metals. They are typically lustrous, that means shiny. They are malleable, meaning you can hammer them into thin sheets, and ductile, meaning you can pull them into wires. They are also sonorous, they make a ringing sound, and of course, they are great conductors. Nonmetals, as you can see on the right, are pretty much the opposite in every way. Now, this slide is extremely important. This is where examiners love to ask questions, the exceptions. You see, mercury is a metal, but it's a liquid at room temperature. And alkali metals like sodium are so soft you could cut them with a knife. On the other side, you have iodine, a nonmetal, which is actually shiny, it's lustrous. And graphite, which is just carbon, is a very good conductor of electricity. Please make a note of these. They often appear as one-mark questions. So physical properties are just one part of the story. To really truly understand metals and nonmetals, we have to look at their chemical properties. It's how they react that really defines their fundamental nature. We can understand the chemical properties by following the reaction journey of a typical metal. It usually starts with how it reacts with oxygen from the air, then how it reacts with water, then with acids, and finally with other metal salt solutions. So let's start with oxygen. Most metals will combine with oxygen to form metal oxides, and these metal oxides are generally basic in nature. Now, here is a very special category, and keyword you must remember for your exams: amphoteric oxides. What are they? Well, they are special metal oxides that can act like an acid and a base. The two examples you absolutely must know are aluminum oxide and zinc oxide. And here is another very important exception you need to be aware of when we talk about reactions with acids. When a metal reacts with nitric acid, or HNO3, it usually does not produce hydrogen gas. Now, why is that? It's because nitric acid is a very strong oxidizing agent. Only two metals, magnesium and manganese, can react with very, very dilute nitric acid to give hydrogen gas. Please remember this. So, with all these different reactions, how do we keep track of which metal is more reactive than another? Well, we organize them into a ranking system. This is what we call the reactivity series, and it's our rulebook for predicting what will happen in a chemical reaction. This series is the absolute key to predicting displacement reactions. As you can see, potassium is right at the top. It's the most reactive. And as we go down, the reactivity decreases, with gold at the very bottom being the least reactive. Now, the rule is simple. Any metal can displace, or kick out, a metal that is below it in the series from its salt solution. The higher up it is, the more powerful it is. Okay, let's apply this knowledge. Here's a classic question. What happens if you put an iron nail in a blue copper sulfate solution? Let's use the series. Just take a moment to think. Where is iron and where is copper? Iron is higher up than copper, so it's more reactive. That means iron will displace copper from the copper sulfate solution, and the blue color of the solution will fade and turn into a light green. So, we've talked about reactions, but what is actually happening at the atomic level? What are the atoms doing? Well, it all comes down to a very simple story of giving and taking electrons. Let's take the formation of common salt, sodium chloride, as our example. Sodium is a metal, so it gives away one electron. When it loses a negative electron, it becomes a positively charged ion, which we call a cation. Chlorine, a nonmetal, accepts that electron. When it gains a negative electron, it becomes a negatively charged ion, or an anion. And it's the strong force of attraction between this positive and negative ion that holds them together. That's your ionic bond. Now, all the properties of ionic compounds are because of this incredibly strong bond. It makes perfect sense, right? Because the force is so strong, they are hard solids. Because the force is so strong, you need a lot of energy to melt them, so they have high melting points. And remember this very important point. They only conduct electricity when they are molten or dissolved, because only then are the ions free to move around and carry the charge. In the solid state, they do not conduct electricity. Now let's see how we can use all this knowledge of reactivity in the real world. Specifically, to extract pure metals from the earth. This entire field is called metallurgy. The entire process of metallurgy can be broken down into 3 main stages. First, we concentrate the ore, which is basically cleaning it and removing impurities. Then we do the main step, the extraction of the metal from this concentrated ore. And finally, we refine the metal to make it very pure. Now, the most important thing to remember is that the method we choose for extraction depends completely on where the metal is in the reactivity series. You see, this connection to reactivity is everything. For the highly reactive metals at the top of the series, like potassium and sodium, we need a very powerful method like electrolysis. For the metals in the middle, like zinc and iron, we can use a simpler chemical reduction with carbon. And for the least reactive metals at the bottom, like gold, well, they are so unreactive, they are often just found in their pure, free state in nature. And for our final section, we will talk about the degradation of metals, which we call corrosion. And most importantly, we will discuss how you can protect your Mark Sibby exam by getting this topic right. So first, let's understand corrosion by looking at the rusting of iron. The main takeaway from this diagram is very, very simple. For iron to rust, it needs 2 conditions to be met at the same time. It needs both air, specifically oxygen, and water. If you remove even one of these conditions, as you can see in the other test tubes, the rusting will stop. So how do we stop it? Well, there are several methods. Simple ones like painting or oiling just create a barrier. But a very important method is called galvanization. This is when we coat iron with a thin layer of zinc. Now, because zinc is more reactive than iron, it corrodes first. It sacrifices itself to protect the iron. Another excellent method is making alloys, like stainless steel. Now, let's talk about exam preparation. It's important to focus your final revision on these high-weightage topics. Questions based on the reactivity series, the formation and properties of ionic compounds, the steps of metallurgy, and corrosion prevention are almost always asked, and they carry more marks. Please be very careful about these common errors. A lot of students forget the exceptions we discussed at the start. They also get confused between calcination and roasting. Just remember, calcination is for carbonate ores, and it's done in limited air. Roasting is for sulfide ores, in excess air. And please, never write that ionic compounds conduct electricity in their solid state. To score full marks in your exam, you must use the correct scientific language. Using these specific terms in your answers, like malleable, amphoteric, ionic bond, metallurgy, galvanization, it shows the examiner that you have a very strong command of the subject. So try to use them wherever they are relevant. And that brings us to the end of our complete revision of this chapter. Now, to leave you with a little food for thought, which single property of metals do you think is the most vital for all the technology we use every day, and why? Thinking about questions like this really helps to deepen your understanding. All the very best for your preparations.